Okay, so the whole reason that we cover inverse relationship, inverse functions, and composition really kind of sets the stage for exponential functions as well as what we call logarithmic functions in the next section. So we've worked with exponential expressions where we have a number raised to a power, okay, where the exponent is a rational number. An exponential function is one where the exponent is the variable. And then our rational number is going to be the base of that expression. So we have the expression b to the x. All right? B stands for the base. That's going to be a rational number. And then x is our input, our variable, the independent variable, and can be defined for all real numbers, including irrational numbers. We can have irrational numbers, the exponent. So when we look in function notation for f of x equals b to the power of x, b has to be positive and it cannot be 1. Okay? It can be any other positive number as long as it is not 1. And then x has to be real. And then we'll have an exponential function. Okay? So what we're going to do is we're going to look at some graphs of exponential functions. We're going to look at some trends that we see among those. And then we'll move into solving some equations with exponential functions in them. So we're going to start by graphing f of x and g of x on the same set of axes, and we're going to use a table of values like we do whenever we first look at a graph. And so what we do is we've got inputs and we've got outputs. We've got x and we've got f of x. All right. So when we're doing a table of value, what are some good numbers that we can use for our inputs when we're trying to explore what a graph looks like? 0, 1, -1, 2. Okay. So we've got some really good values to start with. So let's do -2, -1, 0, 1, and 2. All right. And we're going to evaluate each of those to figure out what our ordered pairs are. So if I take 2, I'm going to raise it to the -2. I'm going to take 2 and raise it to the -1. I'm going to take 2 and raise it to the 0. I'm going to take 2 and raise it to the first, and 2 and raise it to the second. All right, let's actually start from the bottom and work our way up. Nice and easy. 2 squared. 4. 2 to the first power. 2 to the 0 power. 1. Anything to the 0 power is always 1. All right. Now, negative exponent rule. 2 to the negative first power equals, think about what that negative exponent does. It's not going to change the sign. And then 2 to the -2. Not going to change the sign. From 2 to 1/2, 2 to the negative first is 1/2. 2 to the -2. 1/4. Okay? So we've got some ordered pairs. We've got 2, 4. 2, 4. We've got 1, 2. 1, 2. We've got 0, 1. 0, 1. -1, 1/2. -2, 1, 4. Okay? You can use your calculator, but I want you to evaluate these next ones for me. Okay? 2 to the -3rd. What's 2 to the -3rd? 1/6. $100 calculators in your backpack or on your desk. Experiment here. Please participate. To the -1/3. It is going to be a decimal, but I'd like the fraction. Two to the -1/3. Was 2 to the -1/3. Or, I'm sorry, 2 to the -3. I don't know why I keep saying 1/3. Sorry. I realized I was saying 1/3. Because I had a fraction in my head. 2 to the negative 3. 1/8. 2 to the negative 4. 2 to the negative 4. 2 to the negative 5. 1/32. 2 to the negative 6. What's happening to these numbers? Sort of. More generally, what's happening to the numbers? I'm getting 1/8, 1/16, 1/32, 1/34. They're getting smaller and getting closer to what value? 0. Our exponential curve will always get closer and closer to 0, but it will never reach 0. Because there's no exponent I can raise a number to that will give value. I can't raise some power and get a negative number. So it will approach 0, but it will never reach 0. The line y equals 0. Okay, that's our x-axis, right? The line y equals 0, we call that an asymptote. It is a line where our function approaches forever and never reaches. It gets infinitely close to it without ever reaching that line. Asymptote. Asymptote. Okay, now let's graph g of x. Okay, same thing, but now it's 4 to the negative second, 4 to the negative first, 4 to the 0, 4 to the 1, and 4 to the second. All right, what is 4 squared? We'll start at the bottom, nice and easy. 16, what is 4 to the first? What's 4 to the 0? What's 4 to the negative first? What's 4 to the negative second? There you go. Okay, so 4/16, that's way off my graph, but 2/16 is way off my graph, but 1/4 isn't, so I've got that. And then I got a point way up there. And then I've got the point 0, 1. 0, 1. Keep my blue dot, I need that. I've got negative 1, 1/4. Got negative 2, 1/16. Okay? And it'll follow that same pattern where that value, that output's going to keep getting lower and lower and lower as we keep putting in bigger and bigger negative values. So we get this curve right here. Okay? A couple points that are very, very important. And I'm going to talk about them more in detail later. Specifically, the points 0, 1, 2, 1, I'm sorry, 1, 2, 1, 2, and the point 1, 4. Those are some very, very special points. We're going to talk about those. B, same idea, but now we have a fraction instead of an exponent.
Where are you getting your points from? Like,
So we picked our x values because we're like, hey, let's figure out what values we want to use to see what our graph does. So I picked 0 because it's a good starting point, 2 values below and 2 values above. Plug them each into the function. That gives me the output. So this is the point negative 2, 1/4. This is the point negative 1, 1/2. This is the point 0, 1, 2, 1, 2, 2, 4. And then for g of x, it's negative 2, 1, 6, negative 1, 1/4, 0, 1, 1, 4, 2.
so whenever we pick them,
Because we're deciding, I'm going to take x. I'm going to pick some numbers for x. I'm going to plug them in to the function. And I'm going to see what my output is, figure out what y is based on the value. So we'll do the same thing for b. Okay? We'll do our table of values. And we're going to start with negative 2, negative 1, 0, 1, and 2. Just like before. And we'll go ahead and we'll do f of x. So we're going to have 1/2 to the negative 2. 1/2 to the negative 1. 1/2 to to the 0, 1/2 to the 1, 1/2 to the second. Okay, we'll start at the bottom nice and easy. 1/2 squared. Squared. 1/2 squared, y'all. What's 1/2 times 1/2? 1/4. 1/2 to the first power. Not a trick question, y'all. Thank you. 1/2 to the 0. 1. 1/2 to the negative first. 2. 1/2 to the negative 2. 4. So we've got our ordered pairs. -2, 4. -1, 2. 0, 1. 1, 1/2. 2, 1/4. Any guesses on what 1/2 to the third is going to be? Following that pattern? To the third power. So keeps getting closer and closer to the x-axis, but in the other direction. And so we go, and we still have that asymptote on the line y equals 0. Right? So let's pause here and compare the graph of 2 to the x versus 1/2 to the x. What do we notice? It flips it, right? Instead of going up and to the right, it goes down and to the right. We call this on the left exponential growth. And on the right, we call this exponential decay. Always gets smaller and smaller and smaller. All right, let's do g of x. G of x. So now we've got 1/4 to the -2, 1/4 to the -1, 1/4 to the 0, 1/4 to the first, 1/4 to the second. 1/4 to the negative second. Or 16, yes, sorry. 16, and then 1/4 to the negative first. 4, and 1/4 to the 0. 1, 1/4 to the first. 1/4 to the second. 1/16. So then we've got our new ordered pairs. -2, 16, that's way off my graph, but -1, 4 I've got here. I can fit that, and there. And we've got 1, 1/4, and 2, 1/16. And so we can draw our graph, and we see the same relationship that we did with the two f of x's as we do the g of x's. We have that decay instead of that growth. We'll talk more about that in a minute, about why that happens. Okay? Now, special points. Again, I've got the point 0, 1. I've got the point 1, 1/2. I also have the point 1, 1/4. Those are special points that appear on every parent function of an exponential graph. We call those points, first of all, we have the y-intercept is always going to be 0, 1. Because any base raised to the power of 0, our x value is 0, is always 1. So every parent function of an exponential has a y-intercept of 0, 1. There will be no x-intercept because of that asymptote. It will always get closer and closer and closer to the x-axis without ever actually reaching the x-axis. Therefore, we will have no x-intercepts. Okay. The other point that I pointed out, 1, 2, 1, 4, 1, 1/2, 1/4, that is the point that is 1, b. We will always have that point, 1, b. 1 in the base. Okay? So if my base is I'm doing 2 to the x power, I'll have the point 1, 2. If I'm doing 4 to the x power, I'll have 1 comma 4. If I'm doing 10 to the x power, I will always have the point 1 comma 10. Whatever the base is, that's the point that I'll have. Okay? And so these points are always very, very common on exponential graphs. And so we use those as kind of starting points. When we did transformations with quadratics, we always used the points 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4, because those points were common on every parent function. And then to graph other quadratics, we transformed those points. By knowing these 2 points as well as the existence of the asymptote allows us to do the same thing with exponential graphs. We can graph transformations of the parent by taking these points and this line and shifting them in order to get the new location of our graph. So we know that our parent function, if I have my parent function of 2x, or x to the 2 to the x, I'm going to have the points, my y-intercept is 0, 1. I'm going to have the point 1 comma my base, and I have an asymptote at y equals 0. I have those 3 features for that function. Now if I'm taking the function f of x equals 2 to the x plus 2, it's going to move my graph. It's going to take that parent function that we had above, and it's going to shift it. Okay? Think of the exponent like the grouping that we did with quadratics. When I was graphing a quadratic transformation and I had x plus 2, where did that move my graph? To the left. So I'm going to take my parent function up here, and I'm going to move it 2 to the left. So my parent function starts at my y-intercept at 1, 2, and it keeps going up and up and up, and then it always, and then it approaches this asymptote. All right? If I'm going to the left 2, it's a horizontal shift, all of these points are going to move 2 to the left. 1, 2, that's too far, that's 3, 1, 2, and then I get a new graph that is shifted 2 units to the left. Hold on. Let's prove it. Let's show it, right? Let's say, okay, we've got some x values and we've got some y values. Okay, let's find it, all right? I want to see, do these points actually match up where they should be? So -2, -1, 0, 1, all right? And let's plug them in to this function here, all right? So we'll take 2 to the -1st plus 2, or -2nd plus 2. What's -2 plus 2? 0. What is 2 to the 0 power? 1. So we get the point -2, 1. Let's do the same thing with -1. 2 to the -1st plus 2. Okay, what's -1 plus 2? 1. And 2 to the 1st power is 2. So now I have the point -1, 2. Then I can do 2 to the 0 plus 2. What's 2 to the 0 plus 2? 4. And now I have the point 0, 4. And I can do the same thing with 2 to the 1 plus 2, which is 3. And 2 to the 3rd is 8. So I have the point up here, 1, comma 8. So we can use that table of values and see, okay, where my graph is going to be. But if we utilize those transformations that we did with quadratics, I want you to remember that those transformations apply to every single function. Every single one. If we are adding or subtracting to our variable x, that is a horizontal shift, left or right. If we are adding or subtracting to our function outside of x, what does that do? If I'm adding or subtracting to our function outside of x, what does that do? Up or down, or down. Those transformations apply whether we have a quadratic, a cubic, an exponential, a logarithmic, a cosine curve, a sine curve, a tangent curve, all of them. Joe, your question.
Yeah, so how do you do starting points?
Green points, they are the points that we graphed earlier. I already graphed f at 2. So I just took those points again. And then I saw that those points had a consistency here. I always have a y-intercept of 0, 1. I have another point of 1, comma, whatever the base is for the exponential. So if I had the exponential 5 to the x, I'm going to have 2 points. I'm going to have 0, 1, and I'm going to have 1, 5. If I had 7 to the x, I'm going to have 0, 1, 1, 7. If I had pi to the x, I'm going to have 0, 1, and I'm going to have 1 pi. I will always have those 2 points on every exponential before I add or subtract or multiply by anything else. We'll always start with that. All right? So, g of x, I have 2 to the x minus 3. I'm subtracting 3 from the function. So what is that going to do to my graph? What's that going to do to my parent function? It's going to go down 3. Okay? So I've got, this is my parent function again. I'm just copying those points from before. Okay? That's my parent function. And I'm going to take everything, I'm going to move it down 3. So I've got the point 1, 0. I've got the point 1, 2. I also have this y equals 0 as my asymptote. Notice my asymptote did not change over here. Okay? My asymptote did not change. It's still approaching 0 because all I did was I shifted it left. If I take a horizontal line and I move to the left, it's still just that horizontal line in the same spot. But if I'm taking everything and I'm moving it down, that changes the y values, including the asymptote that is y equals 0. So if I take the point 1, 0 and I move it down 3, where's that new point? If I move it down 3, where do I end up? Down 3. Does that change the x value or the y value? The y value. So 1, 0, go down 3. Oh my goodness. I'm 0. Okay. 0, negative 2. Much better. 0, negative 2. We move down 3. 0, negative 2. 0, negative 2. We went down 3. What about the point 1, 2? Move down 3. Where does that end up? Negative 1. Down 3. Down 3. Down 3. And I could keep going down 3 on all those points. And if I take this horizontal asymptote and I move it down 3 from y equals 0, where is it at now? Y equals 0, move it down 3. Where does it end up? And so now my asymptote is down here. So my exponential curve is not going to approach 0 anymore. It's going to approach negative 3 because we're taking all of those values that we get and we're subtracting 3. So it's going to end up moving it lower. So those transformations that we did with quadratics apply to everything. All of our functions. Doesn't matter what you get. Now we're just going to spend the rest of the time looking at some problem solving. So exponential equations have this special thing we call the uniqueness of b to the x. And we can use it to solve some basic problems. And then for more complex ones, we'll use logarithms next week to evaluate. So because the exponential function y to the dx is 1 to 1, again, our base has to be positive. Our base cannot be 1. If I have 2 equations where the base is the same, the exponents have to equal each other. If 2 expressions equal each other and the base is the same, then the exponents have to be the same. That is the uniqueness. And so a lot of times when we have exponential equations, what we do is we rewrite them so that both sides are exponential expressions with the same base. So I want to solve 2 to the x equals 16. What I need to do is I need to rewrite 16 as an exponential expression with a base of 2. So 2 to what power equals 16? 2 to what power equals 16? 4. 2 to the 4th power equals 16. So because I have something to a power equals the same thing to a power, these powers have to equal each other. So x has to equal 4. Let's do it with a little bit more complex situation, okay? I have 9 to the x, okay? And I have 27. Does 9 to any power equal 27? No. But can I rewrite 9 as something else with an exponent? How can I rewrite 9? I'm not going to divide by 9. I'm not doing any multiplication. What number? Give me a number to a power that equals 9. 3 to the second, right? So 9 to the x is the same as 3 to the second to the x power. All right. Can I rewrite 27 as 3 to a power? 3 to the third, right? 3 to the third. Okay. Well, now, since I've got 3 to the second to the x, I can apply my power rule, which says we multiply those together. So 9 to the x is the same as 3 to the 2x equals 3 to the third. Now, because my bases are the same, the uniqueness rule says that my exponents have to be equivalent. So 2x has to equal 3, meaning x equals what? 3, what does x equal? 3 halves. 3 halves. So that's how we use the uniqueness rule. We rewrite both sides so they have the same base, and then we take the powers and we equal them to each other. Can I rewrite 81 as 9 to a power? 9 to the second. Now that the bases match, we can use our uniqueness rule. 2x plus 1 has to equal 2. So 2x equals 1, x equals 1 half. Set the bases to be the same by using exponents. Set the exponents equal to each other. Okay, 1 to the 27, 1 over 27, and then I have 3 to the 2x. What kind of exponent can I use that'll get rid of that fraction and turn it into an integer? What exponent rule turns fractions into integers and integers into fractions? So if I take 27 and I put it to the negative first, okay, 1 over 27, 27 to the negative first, those are equivalent fractions. Because the negative makes the reciprocal. Now, I want to turn 27 into a 3. So what exponent, what base and exponent am I going to use? 3 to what power? To get to 27? I cannot hear you. 3 to the third to negative 1. I can't hear that well, so I really don't understand. And then, so 3 times negative 1, that gives us negative 3 equals 3 to the 2x. Now that our bases match, we can use our uniqueness rule to solve for x. Negative 3. So we'll be using our exponent rules in tandem to get to that uniqueness, and then we get to solve an algebraic equation. More complicated exponential equations will be solved using logarithms, which is something that we'll cover in the next section, when I can't get that uniqueness. Now, lots and lots of real-world problems are modeled by exponential equations. So many times, okay? Most common, compound interest and half-life, okay? Compound interest formulas determine the amount of money that is either accumulated in a savings type account that gain interest, or how much interest is owed when you borrow money. Okay, compound interest is used to determine that. Half-life are formulas that determine how much of the material is left after a certain amount of time. So like radioactive material breaks down because it's unstable, and the half-life says how long it takes for half of that material to decay. So the material gets cut in half, then it gets cut in half, then it gets cut in half, then it gets cut in half, breaking it down over time. Okay? And so those are exponential equations. Exponential growth, because it's getting larger, versus exponential decay, because it's breaking down. There's a couple different ways that we can get growth or decay equations in exponentials. Okay? When we first did these up here, we had growth on the left and we had decay on the right. What is the major difference between our growth equations and our decay equations? The growth equations compared to the decay equations. Right, but what about the equations? What about the equations is the notable difference when we end up with... One has fractions, the other has integers. So when we have a base, okay, a base that is greater than 1, that gives us growth. When we have a base that is less than 1, but again it has to be positive because we can't have negative. When we have a base that's between 0 and 1, then we have decay. The other way that we can get it is with the exponent. If the exponent is negative, then we have decay. If the exponent in the equation is positive, then we have growth. Okay? Okay? And so we can look at the equations and kind of determine so that we know what to expect. Am I going to get a growth equation where it goes up and to the right, or am I going to get a decay equation where it goes down and to the right? So let's look at each of these, and we're going to classify them as either growth or decay. Y equals 3 to the x. Growth or decay? Growth. How do we know? It's not a fraction, and my exponent is positive. We have growth. Okay? Base is greater than 1, and the exponent is positive. Growth. What about the second one? Growth or decay? Ooh, it's not decay. It's growth. Why is it growth? It's greater than 1. Greater than 1. Growth. Third one. Why? Negative exponent. We have a decay formula. Fourth one. Decay. Why? Less than 1 base. Third one. Or fifth one. Last one. Now, if I had 0.5 to the negative x, that would be growth. Because it's decay and then it's getting flipped to make it growth again. It's weird. So don't stress about that. Yeah. If I had a base that was less than 1 and then a negative exponent, what it does is the base makes it decay and then the negative flips it to make it growth again. Kind of cancel each other out. All right, so solving some formulas. At this point, it's just plug and chug. I'm not going to make you write exponential equations, but when you get to more advanced math, you will learn a pattern for writing an exponential equation based off information given. You'll also see on the SAT, that's something that shows up quite a bit, is they say which of these equations models this scenario. And so you have to be able to write your own exponential equation based off of the scenario. We don't have time to go into all that detail, but that's something that you will see. For now, it's pretty much just plug and chug. I'm going to be giving you the formulas. You just need to figure out where they go. We've covered compound interest before. The formula A equals P times 1 plus R over N to the NT. It's been a little while, but we've done it. Find the total amount invested in a savings account. If $5,000 was invested and earned 6% interest compounded monthly for 18 years, round your answer to 2 decimal places. We've been given the compound formula. 5,000 refers to which part of this formula here? P stands for principal. Okay? So in order to find our amount, we will take 5,000, our principal, and we will multiply it by 1 plus. The 6% refers to what part of the formula? The rate, R. What do I need to do with 6% before I write it in my formula? turn into a decimal, which is what? 0.06. Okay? Compounded monthly refers to what part of the formula? Compounded monthly refers to n. 12 times a year. So n is 12. And then to the 12 times, 18 years refers to what part of the formula? T. So 12 times 18. All right. So we can evaluate that. Simplify it a little bit. We get 5,000 equals 1.005 to the power of 216. The power of 216, which gives us approximately $14,683.83. $14,683.83. Okay, so that's the amount of money in the account after 18 years. If we want to find the amount of interest that was earned, we would just subtract the total amount by the principal, 5,000, and we would get $9,683.83 in interest earned if we subtracted the 5,000 that was initially put into the account. Accidental oil spill of radioactive material, not an oil spill, an accident of radioactive material, decays at a rate of 5% per day. How much debris remains after 30 days? Use the formula. Okay, so we've got this, we got this, we got this. 100 grams. What part of the formula do we think that applies to? The A. Y equals A. That's usually our initial amount. Then we have our base. The 5% refers to the rate, 0.05 times 30 days. So we'll multiply those. Simplify that exponent and end up being negative 1.5. So 100 times 2.7 to the negative 1.5. Because of that negative exponent, we know it's going to be decay, and we end up with 22.54 grams, approximately. Last but not least, the adult takes 400 milligrams of ibuprofen each hour. The amount of ibuprofen in the person's system decreases by percent. How much ibuprofen is left after 6 hours? We can use this formula here. The only thing we need to fill in is the time. So we've got the initial amount was already put in. The 29%, we have a decay here, 0.71. That's 29% less than 100%. So that's how we get the 0.71. All we need to do now is just fill in the time of 6 hours. And that gives us approximately 51.24